A sample of gas is taken through cycle ABCA, as shown. The net work done on the gas is minus 1.2 joules. Along path AB, the change in internal energy is 3.0 joules, and the magnitude of the work done is 5.0 joules. Along path CA, the energy transferred to the gas as heat is 2.5 joules. How much energy is transferred as heat along path AB and path BC? Let's start by sketching a PV diagram to represent this cyclical process. The gas is initially in state A. Work is done to expand the gas to state B isobarically. Work, and possibly heat, is exchanged to compress the gas to state C. Finally, heat is then exchanged with the gas isochorically to complete the cycle back to state A. It will be useful to look at the work done on the gas in each of the processes that allow it to complete the cycle. Negative work is done on the gas to expand it from state A to state B. Positive work is done on the gas to compress it from state B to state C. And no work is done on the gas to return it to state A. The net work is the sum of the works done on the gas for each of the thermodynamic processes in the cycle. Since there is no work done on the gas from C to A, we can eliminate this term. We see that the net work done on the gas is the sum of the work done in expanding and compressing the gas, which is given as negative 1.2 joules. We should recognize that this work is equal to the negative of the signed area bounded by the processes represented as a cycle in our PV diagram. The first law of thermodynamics states that the change in internal or thermal energy between two thermodynamic states is equal to the sum of the work done on the gas between those two states and the heat exchange during the transition between the states. Looking at the process that takes us from state A to B, we see that the change in internal energy from A to B is equal to the heat exchange from A to B plus the work done from A to B. Since the process from A to B is isobaric, we know that the work done must be negative. Isolating the heat exchanged from A to B, we get that the change in internal energy minus the work done from A to B is equal to 3 joules of internal energy change minus a negative 5 joules of work. This means that the heat exchanged from A to B is equal to positive 8 joules. Now, since the work done during this first process is negative, in order to increase the temperature of the gas, as is what happens for any isobaric expansion, more energy has to be added as heat than is taken away by work. So this makes total sense that the heat exchanged is positive 8 joules. Let's use this to now determine the heat exchange from state B to C. The evolution from B to C involves a compression of the gas. In order to find this, we'll need to know the work done on the gas and its change in thermal energy as related by the first law of thermodynamics. We know that the total change in thermal energy for the complete cycle must be zero. So, the change in internal energy starting at state A and ending at state A is the sum of the changes in internal energy between states A and B, states B and C, and states C and A. The first law of thermodynamics demands that the change in internal energy from state A to state B is equal to the sum of the heat exchanged with and the work done on the gas between those two states. The change in internal energy from state B to state C is equal to the sum of the heat exchanged with and the work done on the gas between states B and C. The change in internal energy from state C back to state A is equal to the sum of the heat exchanged with and the work done on the gas between those two states. The sum of these works and energies for a complete cycle must be zero. Let's group the heat terms separately from the work terms algebraically. We can recognize that the sum of the work terms is equal to the net work done in this process. So, the sum of the heats plus the net work is zero. Let's isolate the heat exchanged with the gas from states B to C. I'd like to really factor out that minus sign. Now that we have taken this as far as we can possibly go algebraically, let's plug in numbers. Putting this into my calculator, I get that 9.3 joules of heat was transferred away from the gas when it was compressed between states B and C.